Start without all of your permissions. I hope that's okay.
That's fine with me.
All right, so can you see my hand and pencil and stuff?
Yes.
Okay, all right. All right, so this is number 25 from 9-2, and it says g of x equals e to the x minus 1 over x, all right? So this is how I'm going to come up with a series for this. First of all, I'm going to write, what is e to the x? Do we know what e to the x is? 1 plus x plus factorial plus 3 factorial plus dot, 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 right? Minus 1 all over x, right? So g of x is equal to, what happens to the 1 and the minus 1 here? They get blasted away and zeroed out here. And then if I were to divide every one of these terms by x, what do we get? Well, we get x over x, which is 1 plus x over 2 factorial, right? Plus x squared over 3 factorial, sorry. Over 3 factorial plus dot, 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 plus, and then I'm going to come up with an nth term. X to the, well, this is going to be, would you say n minus 1 maybe? N minus 1 over n factorial? Does that work? Okay, yes. Plus dot, dot, dot. If I were to make that a sum, that's going to be, I'm going to start at n equal 1. Let's see what happens, to infinity. And then x to the n minus 1 over n factorial. Do you agree with that? I mean, that's kind of what I would do.
Oh, wait, can you do n over n plus 1, like x to the n over n plus 1?
Yes, you can. If you start at n equals 0, sure.
Because that's, okay.
Yeah. Yes, you can. All right, so what did the question say? It said, find the first 4 non-zero terms. Well, I only found the first 3, right? So the first 4 would be what? Let's write those down. And, the AP people are going to want you to list them instead of, you know what I mean? To me, this is clear. But anyway, so 1 comma x over 2 factorial comma x squared over 3 factorial. And we can follow the pattern, right? Comma x to the third over 4 factorial. I'm just listing the first 4, okay. Right? And then the general term's going to be x to the n minus 1 over n factorial, or it could be x to the n over n plus 1 quantity factorial, right? All right, so that's part B. Part C says for the function g in part B, find g prime of 1. So this is part B. I'm going to do C now. We want g prime of 1. Well, they didn't really tell us how we have to find g prime, did they? So I'm going to take the derivative of this using the quotient rule. So here we go, ho, which is x, d high, which is e to the x, minus high, which is e to the x minus 1, d ho, which is 1, all over ho, ho, which is x squared. And if I, such that x equals 1, right? Because I've got this as a 1 here. So let's put 1 in. What do we get? We get e minus e plus 1 over 1 equals 1. So g prime of 1 is equal to 1. But they want us to use that information to prove this. So they say, well, what is this? N over n plus 1 quantity factorial equal 1? Question mark. This is n equal 1 to infinity. Well, I don't know what this is, but I do know what this is, right? So, yeah, I think your way is going to work better. So I'm going to take this and bring it down here and just do a little bit of work here. We're going to say the sum from n equal 1 to infinity of x to the n minus 1 over n factorial. Can I write this another way? Go ahead and tell me there.
Wait, but then it would be n equals 0.
I know, that's all right.
Okay, so
that's all right. It's gonna work.
N equals 0 to infinity of x to the n over n plus 1 factor.
Right, okay, good. Oh, instead of 1, I see. All right, but what we're gonna do, we're gonna take the derivative of this. Well, which one do you want to take the derivative? Doesn't matter. We'll do both, okay? So the derivative, let's say this is g. G prime of x is equal to, well, what's varying here? It's just x, right? So this is going to be equal to the sum, and I'm going to leave the indices off. What do? We bring power down, n minus 1, x to the n over n factorial, right? This one, let's see which one's going to help us better. G prime of x is going to be what here? The sum, it's going to be n times x to the n minus 1 over n plus 1 factorial. This one's going to help us out better. Why? Because does this n over n plus 1 look familiar? Do you see this?
Oh, yeah.
Okay, now what we have to do is make sure that the G prime works, okay? So what happens if I let n equal 0 here? I get x to the negative 1, and this wipes out. So I need n to start with 1. Now, when you take the derivative of a series, usually if you start at 0, your next series is going to start at 1. And if you take the second derivative, your series is going to start not at 0, it start at 2. Okay, when you integrate, you don't have to worry about that as much. Because what are you doing? You're subtracting 1. So that makes sense that you would maybe start at a different one. So then we're going to start at 1 and go to infinity here. Okay, so if this is g prime of x, which is equal to the sum from n equal 1 to infinity, and that's n x to the n minus 1 over n plus 1 factorial, what happens when I want g prime of 1? And I stick 1 where the x is. N equal 1 to infinity, and we get what here? N over n plus 1 factorial. Oh, so what does that have to equal? 1. See how cool that is? That's kind of a cool thing. And when I was working the sequence and series packet, there's another one in there that matches it, but it was making me pull my hair out when I was working it.
Oh, yeah. Is that on Moodle?
It is. It is. It's number 11 on the Maclaurin series here, where it says for the function g in part b, find g prime of negative 1 and see that it equals the same sum. Do you see how that mirrors that one?
Which number?
It's number 11 on the Taylor polynomial and Lagrange error bound. It's, I don't know what page, it doesn't, they're not numbered. Number 11. It's at the bottom of a back page. I can count what page it is, hang on. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. Page 20? Could it be page 20? I think it's page 20.
It's the let f be the function given by f of x equals e to the negative
Yep.
x. Okay.
Yeah, but that's a very similar problem. So the strategy is to take the derivative of that g and then set it equal to the series, like that you find here. The same strategy that we had with this one. So yeah, do you see it on Moodle now?
What's it?
It's at the very bottom of the review stuff.
Oh, okay. I see it.
I've got the blank copy, and then I have. It wouldn't let me scan in. I had 20. This is 22 pages. This packet.
It is.
And then I had all of my backup work, so you could see my work on 12 other pages, and it wouldn't let me scan them all in. That's why I have 2 documents there.
So it's sequence and series review answers and then work for answer.
Yes, I couldn't get it in one document. The document was like the size of the Great Pyramid of Giza. Right? But yes, they're all up there now.
Okay, I see it.
All right, any others?
Number 33 on the 9-2 homework.
33. Says, what is the coefficient of the x minus 2 to the third in the Taylor series for natural log of x at x equals 2? Okay. So my function, this is 9-2. I'm sorry here, 9-2. Number 33. My function is what? Y equals natural log of x. I always do that. Make my natural logs h's. Right? And we're centered at 2.
Are you doing number 3?
I'm doing 33.
Oh, okay.
I just didn't write the 3. I was so excited to get to the problem.
Oh.
That's the truth. Okay, so I don't know what the Taylor polynomial is, so let's do some derivatives here. We get y equals ln x, y prime equals 1 over x, right? Or x to the negative 1. Y double prime is equal to negative 1 over x squared, right? Which is negative x to the negative 2. Y triple prime is equal to 2 over x cubed, yes? And I don't need the whole Taylor polynomial. I just want the part that is for the x minus 2 term, right? So I need y triple prime at 2, because that's the center. So y triple prime of 2 is what? 2 over 8, which is 1/4. Yes. Okay, and then what would so my polynomial is going to be f of x equals f of 2 over 0 factorial plus f prime of 2 over 1 factorial, 1 factorial times x minus 2 to the first plus f double prime of 2 over 2 factorial times x minus 2 to the second plus f triple prime of 2 over 3 factorial times x minus 2 to the third, plus on and on, right? But I just want to know what this coefficient is, don't I? So what do we do? Well, we found y triple prime of 2 is 1/4. I didn't put my fraction here. So I'm going to say the coefficient is 1/4 over 3 factorial, which is equal to 1/4 times 3 factorial, which is really 4 factorial, which is 1 over 24. So that's what they want you to do. So yeah, sometimes there are ones you don't know. So you have to generate, whatever derivative you need in order to calculate the coefficient they want. Or follow the patterns. All right. What else you got? Anybody
This
at
is
home?
Lois.
Go ahead.
Can you do 9-5 number 55 and 17?
Hold on. You're 55 and 17. Can we do 17 first and then 55?
Yeah.
Okay. 9-5. Number 17. (9-5), number 17. And that is the sum from n equals 1 to infinity of 3 to the n plus 1 over 3 to the n. And they want to know if this diverges or converges. And they say there are multiple different ways that you can do this. Well, what's the very first test I always choose? I always like to do the nth term test for divergence. Why? Because if I do the divergence and it diverges and I don't get a 0, then what happens? We're done, aren't we? So let's try the nth term test. Okay, well, what is the nth term test? Well, it says you take the limit as n goes to infinity of 3 to the n plus 1 over 3 to the n. And this one, if I do this, the limit as n goes to infinity here, I'm going to bust this fraction up, meaning I'm going to say 3 to the n over 3 to the n plus 1 over 3 to the n. And while this one, 1 over 3 to the n, as n goes to infinity, this goes to 0. What does this one go to? So this equals 1, which is different than 0, which means it diverges. Boom. So the nth term test for divergence is a really nice one if you sense the derivative may be different than 0. Okay? Does that make sense?
Since it doesn't equal.
Yeah, thank you.
You're welcome. I'll do 55 in a sec. Yeah, what's your question there, Mr. Loman?
It has to equal 0 in order for it to like.
No, no. If it equals 0, oh, you got to try another test. It's a test for divergence only. It doesn't make any comment about convergence. So if it's equal to 0, you just go, oh, I got to try another test. You cry and you say, okay, I'll try something else.
I know we're gonna be 55. I had a question on that one too, but the two after this one.
Tegan, do you mind if I do the 2 after this one and then get to 55?
Sure.
Oh, so 19?
Yeah, that's what I was.
I mean, it still might diverge, but like, okay, so for a prime example,
But
okay?
you just know that it doesn't, that it diverges if it's not equal. to
Right.
0.
Like for example, 1 over n. Does that nth term go to 0?
Yeah.
Bummer. You got to try another test because 1 over n is a p series, p equal to 1, and it diverges. It diverges by being a p series, and it also diverges from the integral test because if you find the antiderivative of 1 over x, that's the natural log of x, which is increasing, without bound. So even if it goes to 0, it may still diverge. You just don't know. You have to try something else. Because we know that, see, you can't add numbers that are not getting smaller. We just know that. That's why that nth term test is an nth term test for divergence. And if it's 0, you got to try something else. Okay. I'm sorry, I'm almost done writing. -1 to the n plus 1. And then we have 10 to the n to the 10th. Okay. Now, I know that we might know, right? When we did relative rates of growth, do we remember whether 10 to the n one or the polynomial one? If you were going to do L'Hopital's rule in your head.
I think the one on the top one.
Yeah, because the derivative of an exponential never goes away, right? It would be ln of 10 times 10 to the n. Ln of 10 quantity squared times 10 to the n, right? I mean, that's never going away. But this polynomial is going to go to 0 eventually, right? Okay. It's an alternating series, but I want to do the ratio test. Are you okay with that? Because I already know, that this is going to go to infinity. Everybody, I hope, has an instinct to know that that's going to blast off to infinity using relative rates of growth, which is from the January. Was it January? I think it was January. All right, anyway, here we go. So using the ratio test, and whenever I have an exponential and some kind of polynomial, I'm using the ratio test because we get pretty fast at this. Okay, so that's going to be the limit as n goes to infinity of the absolute value of, what is that, 10 to the n plus 1 over n plus 1 to the 10th times, I'm going to flip it already, n to the 10th over 10 to the n. And then the 10 to the n's cancel. And if I rewrite this with the n's together, the limit as n goes to infinity of n to the 10th over n plus 1 to the 10th time, right? I'm just keeping the n's together. And then what is this going to be? Well, I just have a 10 standing alone up here, don't I? Lonely old 10 up here at the top. Well, what about this? What's the degree of the numerator here? It's 10. What's the degree of the denominator? If I were to expand this, although I would be crying because I'd have to use Pascal's triangle all the way to the 10th line, right? But what would the highest one be?
The 10.
N to the 10th. So this is degree 10 over degree 10, which makes this ratio 1, right? Yes? Do we agree that this limit here is 1? So this is equal to 10, which is greater than 1, which means diverges. Because if it's equal to 1, the ratio test doesn't work. It's inconclusive. If it's greater than 1, that means your numbers are getting bigger and bigger and bigger, right? Because the R is starting to behave like tens, right? So it diverges. Yeah. Convergence means, okay, so converge, you can find the sum.
Okay.
You can find the sum, although sometimes it's really hard to find the sum. So sequences are different, like a list of numbers may converge to a number.
Okay.
And then series, if it converges, it's just like the integrals. The integrals converge if you can find the answer, right? The improper integrals, if you get a number. If they go to infinity or negative infinity, they diverge. It's the same thing as integrals, okay? All right, does that make sense? Yes.
Could you use the alternating series test for this?
Yeah, but it's harder, I think. And the reason is that you have to compare 10 to the n plus 1. Oh, it doesn't go to 0. Okay, so that's a great question. Does this limit go to 0? The answer is no. It goes to infinity, right? The alternating series test is a test for convergence only. You know how the nth term test is a test for divergence only? The alternating series test is for convergence. So if you if you busted, the first thing, the limit is infinity, you got to try a different test. Okay. All right. Number 21.
Would you just do the same thing, like ratio instead of alternate?
Personally, I would do the nth term test for divergence. Well, that alternates. But here, this is let me show you what I mean.
Okay.
This is -1 to the n plus 1. And this is ln n. I have a really hard time writing that. I'm sorry. ln n squared. What can I do with this 2?
You can bring it down with 1.
So it's 1/2, right?
So
So if I do the nth term test, right? So I do the nth term test.
Mhm. When you write the nth term test, do you write it as limit as the summation? Do you include the summation or you
Just a sub n.
Okay.
Now this alternates. The nth term test, if I go back, I think they only want it to be positive. I forget where it is. But that limit does not exist because it alternates from 1 and -1. So let's try the alternating series test. Shall we do that? Let's try that. But I want to rewrite it first. N equals 2 to infinity. And what do we get? -1 to the n plus 1. And this is ln n over 2 ln n, right? I can bring that 2 down in front. And what happens? This goes away. And what do we get? We get the sum from n equals 2 to infinity of -1 to the n plus 1 times 1/2. So the alternating series test only tests for, but that limit just doesn't exist. It's going 1/2. No, it's going -1/2 plus 1/2 plus -1/2. So it's alternating. So that limit doesn't exist. I just want to be precise. Let me,
So we just say it doesn't exist.
the limit doesn't exist, right?
Oh, and then because of that, it
Diverges, yeah. It diverges.
You know what that means?
Okay, you know what? It does, the end term test doesn't say it has to be positive.
Oh, okay.
So that makes me feel better.
Because it says it just, as long as it doesn't exist or diverge.
If it doesn't exist or not equal to zero. Yeah. So I would say the nth term test here. The thing that has to be positive, continuous and decreasing is the integral test. And I would do the limit here as n goes to infinity of -1 to the n plus 1 of 1/2. This does not exist because it's oscillating, right? It's oscillating between 1/2 and -1/2. So this diverges because the limit does not exist. Gosh, all of these diverge. That's pretty fun. All right. 55 it is, eh? Well, it is cold here today. We are in the Great White North now, aren't we? With the snow we had yesterday. I know it's not snow white out there now, but we can dream a little bit, right?
It's actually so nice out today, though.
It is nice. I have to agree. With that wind yesterday, it was pretty brutal. Number 55. Number 55 says, find the radius of convergence. And that's the sum from n equals 1 to infinity of n to the n, x plus 2 to the n over 3n over n factorial. So whenever we're trying to find the radius of convergence or the IOC, we have to use only one test, and that test is the ratio test. Yep.
Why do we have to use the ratio?
That's the only way to find the IOC, because that's when it's behaving. I say it's when the series is going to behave geometrically, right? Like the absolute value of whatever your limit is less than 1. That's when it's going to behave geometrically. Okay, and that's when it'll exist or conform to whatever function it's going to be. All right, so we've got a lot of madness going on here. So let's see what we're going to do. Or the limit as n goes to infinity of the absolute value of n plus 1 to the n times x plus 2. Oh, this is the n plus 1, sorry. To the n plus 1 over 3 to the n plus 1 over n plus 1 factorial times, now I'm going to flip this now, which is going to be 3 to the n times n factorial over n to the n x plus 2 to the n. And mercifully, we're done with that big, huge absolute value thing, right? Now, the easy things to see right away, I think, are, well, the 3 to the n is going to go away, and I'm left with a 3 down here at the bottom. And then inside every n plus 1 factorial is an n factorial waiting to be found. So this is n factorial, so we can get rid of one of these. And I'm left with an n plus 1 on the bottom. I can get rid of an x plus 2 to the n, right? Because I've got 1 to the n up here. X plus 2 to the n up here. So I'm going to rewrite this to get some clarity here. We have n goes to infinity, the absolute value of. Now I'm going to rewrite this one because I see there's an n plus 1 down here in the denominator. Do you see that? I know it's really small. Do you see this n plus 1? And I have an n plus 1 here. Can I bust it? May I bust this up into n plus 1 times n plus 1 to the n? Right? So this is n plus 1 to the n times n plus 1. Because if you add the exponents, you get n plus 1 to the n plus 1, right? Okay, times, this is x minus 2 is left up here and nothing over here. Divided by, I have an n plus 1 on the bottom.
Wait, x plus 2.
Oh, it's plus, I'm sorry. I have an n plus 1 on the bottom, and I have an n to the n still. And a 3, yes. I even made a mental note to myself. I wasn't going to forget that 3.
Wait, we do have an n plus 1 on the bottom?
We do, because inside every n plus 1 factorial is I canceled.
Oh, you haven't canceled.
Yeah, I haven't canceled that out yet. But now, because I busted this one up in the numerator, I can cancel these n plus 1s, right? And I'm left with the limit as n goes to infinity of the absolute value. Now I'm going to put the n's together. So we're going to have n plus 1 over n to the n, right? Because they're both to the n.
Yeah.
And then I'm going to have x plus 2 over 3, correct? Now this looks like this would be 1 to the infinity. But I'm going to rewrite this little gem as 1 plus 1 over n to the n. That's one we should know. This is E. This is E. Okay, so this limit then is E times x plus 2 over 3 absolute value. And this will converge when this is, right?
Oh, so that gets, it's the 1 plus 1 over n to the n is e?
Yeah, I should make that broader here. Yes. It's the whole thing.
Okay.
What's the one that equals 1? Is it n plus 1 over?
N over n plus 1 to the n is 1 over e, right? If this inside here is flipped, it's 1 over e. Okay, so I'm going to say now negative 1 is less than e x plus 2 over 3. Oop. So I'm going to multiply everything by 3 over e. Yes? Yes? 3 over e. It just feels weird. Okay, 3 over e less than x plus 2. Or greater than, yeah, well, less than x plus 2. And then that x plus 2 is less than 3 over e. And I'm going to add 2 to everything. Or subtract 2. So this is negative 2 minus 3 over e. I can't say it. That's the problem. And then 2 plus 3 over e. So if I were to do the IOC here, the center is negative 2.
Mrs.
Because I'm
Muller,
thinking-
why don't you subtract 2 on that one side?
This should be a negative here.
Oh, okay.
Okay, so this is negative 2 plus 3e. This is negative 2 minus 3e. And then what is the radius of convergence? Because I think that's what it's asking for. Yes. The radius convergence is 3 over e.
So when it's something really weird like that, you kind of just go with the ratio test and like,
Okay, so whenever it's asking for the interval of convergence
Oh,
or the
okay.
radius of convergence, there's no doubt. You
yeah.
absolutely no doubt about it. You were starting with the ratio test every time.
So, and then for other things, though, like if you're finding if it converges or diverges,
Then it's up to you.
yeah. So it's
But this is
ratio
okay. So
test.
this is a power series. Why is this a power series? It's got an x in it. It's a power function in here, right? If you have ones like we were doing a second ago,
Those are,
these are just series.
So, and for those, is ratio test always just like a good fallback?
Sure.
Okay.
People get used to doing certain things, and then you'll get a feel for, well, that ratio is 1. I got to try something else. And you better be assured that I'm going to make you do multiple. You're going to have to, things are going to turn out to be 1, and you'll be like, oh, rats, I got to do a different one.
What if we just guess the
Yeah, maybe. Yeah, sure. But well, this is how I look at things. I look at like on some of these here, I just look and see like no, this like 22 is telescoping, but we're not ready to go there yet, and you get a feel like this one here, you're going to use the limit comparison test. Why? Because what do you wish that was? I'll zoom in. I'll try to zoom in. What do you wish this was? I wish that was 1 over n, don't you? This one? 1 over, don't you wish it was 1 over n? So that's what you would compare it to. And if you get a number, which you will, you'll get 1/2.
Is 1 over n bigger than that?
No, see, the direct comparison test, you have to know if it's bigger or not. The limit comparison test is you put one over the other, and if you get a number, they behave the same. That's why I like that one more, because I don't have to worry about which one's bigger or not.
So it's better if it's the same degree as
Yes.
the similar one? Okay.
Yeah. With the direct comparison test, you have to know which one is bigger than the other one, or if it's smaller and it can diverges, then the bigger one will diverge. The pressure is you have to state and know that one is bigger or smaller than the other one, which is not necessarily hard to do on some of them, but the limit comparison test is just like you're comparing their relative rates of growth. So if they grow the same, meaning you get a number and not an infinity or a 0, you know they behave the same. Yes.
Can you go back to that other problem for a second that we were just doing?
Yes, sir, of course.
How do you, so
This
once
one.
you get that, or no, the number 55.
Oh, yeah, I'm sitting on it. Hang on here. There we go, sorry. Yes, sir.
Once you get that E, how do you just automatically know that it converges when it's less than 1?
Because the ratio test says, with the ratio test, you have 3 possibilities.
Mhm.
Ratio test, you have, I'll write it here. Ratio test possibilities. 1, if the limit as n goes to infinity of a sub n plus 1 over n plus 1, right? A sub n plus 1 over a sub n is greater than 1, it diverges. If the second possibility is the limit as n goes to infinity of a sub n plus 1 over a sub n is less than 1, it converges. That because then it behaves geometrically, like the geometric series, right? Our r has to be less than 1 for it to converge. And then the third possibility is the one that we don't like because we did all the hard work. And, we get a 1.
Yeah.
And then you say, right? Because I got to do something else. It's inconclusive.
Okay, so like, how do you know that that's less than 1 just by looking at it?
I don't.
Like the E to the x plus 2 over 3?
No. When this absolute value is less than 1, that means this expression has to be between -1 and 1. And for all x's in this range, it
I
is.
see.
Yes.
Okay.
Yeah.
So you're just saying it'll converge if it's less than 1, and then you go make it like that one.
Yes, I'll find out where it behaves like this second one. Yeah. And that's for power series. Yes. What that means, the power series, it means it has its x's in there.
Okay.
If it's a regular one,
Just
like
ends.
with just the ends, yeah, if it's less than 1, it converges. If it's greater than 1, it diverges.
Right.
Yeah. Yep. Mhm. Which one?
It's not one of the tests. I think it's a limit test one. That's whenever you work out.
Sure.
Yeah, I'm on
Okay, so you know what,
3 and 4 on this, but-
which test is it? Do you know?
I think it's the limit one
3 and 4.
because you would compare it to.
No. I'm talking about
Oh,
which test is this on, so I can let the rest of the crowd know. 2020. This is from the 2020, and it's number, move your phone. Thank you, 15.
My bad.
15D, and that's 2n squared minus 1 over 3n to the 5th plus 2n plus 1. Okay. All right, so we're trying to figure out whether this one converges or diverges. Well, first things first. If I did the nth term test for divergence in my head, the degree of the top is what, 2? The degree of the denominator is 5, which means the limit is going to 0. So the nth term test doesn't work for divergence.
What's the question?
Converge or not converge? Okay, so then I would use the limit comparison test here, yes. And now what would I compare it to? I would compare it to what I wish it was, which is n squared over n to the 5th. What's n squared over n to the 5th? 1 over n to the third. Okay, so comparing, I'm going to do LCT, comparing to the sum from n equals 1 to infinity of 1 over n to the third. Now, how did I choose that? Well, because I did this ratio of the biggest and the terms in the numerator and the denominator, and I found out that it was 1 over n cubed, yes? Do I know what this one's doing? That's the other thing with the limit comparison test. Do we know what this one, is this a P series? And this is P series, what? P greater than, which is greater than 1, which means it converges because of the P series. So I know this one converges. So if I get a number when I do the limit comparison test, now I like to put the not so nice things on the top. Now when I say that, this is nice. This one is not so nice. So I'm going to put this in the numerator, 2n squared minus 1 over 3n to the fifth plus 2n plus 1 over n cubed. You just do compare them, just like we did with relative rates of growth. Okay, so if I say the limit then as n goes to infinity of, I'm going to keep change flip. So that's going to be 2n squared minus 1 over 3n to the fifth plus 2n plus 1. Oops, sorry. Times what? N cubed over 1. All right, and I'm going to take that n cubed and I'm going to multiply it in. We get the limit as n goes to infinity of, what is that, 2n to the fifth minus n to the third over 3n to the fifth plus 2n plus 1. And do we know this limit? It's 2/3, isn't it? Because the degree of the numerator is 5, the bottom is 5, so this is 2/3. Is that a number? It's not an infinity. So these two functions behave the same or grow at the same rate. So we can say by limit comparison test, both, I'm going to say converges here. Both the sum of 1 over n cubed, n equal 1 to infinity, and the sum of n equal 1 to infinity of 2n squared minus 1 over 3n to the fifth plus 2n plus 1 converge. But somewhere on the paper, you have to say that this one converges, right? You have to tell the folks that this one converges and why it converges, right? Now, on my key, I may have done 2 over 3n cubed. I don't know, but n cubed, 1 over n cubed works. So why not use the simpler thing? Okay. But did I have to compare whether which one was bigger or smaller? I didn't. See, that's the beauty of the limit comparison test, because I would have a nightmare in my own brain figuring out whether this one was bigger than this one. Do you know what I mean? And that, or that one was, you know? So the limit comparison test takes that pressure off. Because if you get a number like this, then you're golden. And this number doesn't have to be a number less than 1. It could be 10. It could be 25. It could be 30. It could be, 110, whatever the number is. It just can't be infinity or 0. Okay? Because they have to grow at the same rate, right? Yes.
Is there a time when the direct comparison test works, but the limit comparison test doesn't?
I can't think of one now.
Okay, so just
Unless the question says using the direct comparison test, then it wouldn't work. But I'm not going to do that to you tomorrow or Tuesday.
Okay.
Because the limit comparison test is my favorite. So I won't make you choose. Does that answer your question? Yeah.
Can we do this one right here?
That the same one?
Yeah, it's on the same test.
Okay, yeah, sure. Let me write it down. I'm trying to put this in order here, right? 15. This is the same test, 15F. The sum from n equal 1 to infinity of n cubed e to the negative n. Okay. I would do the integral test on this using a table.
So do you use the integral test when you like can tell?
You
that
can integrate it.
integrated?
Yes. Yeah, I know that's not the, well, that's, okay, so, what do I want to compare this to? I want to compare this to, x to the third e to the negative x dx. So what are the, in order to do this, what do I have to know? I have to know that this function is positive. Well, x cubed, when x is going from 1 to infinity, is positive, right? I have to know if it's continuous, and it is. And I have to know if it's decreasing. And so is e to the x going to win the battle to 0? The answer is yes. So it's decreasing. Because this is the same as saying x cubed over e to the x, right? And this is going to be decreasing. It has to be, right? Because x cubed, if you do this, and e to the negative x, that goes to 0 faster than x cubed. Remember, when we did that nice little presentation on what grows fastest and what goes slowest, e to the x grows really, 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 really fast, right? And so decay is also really, 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 really fast compared to a polynomial. All right. So I'm going to do an integration aside. That's what I call it. So I can figure out what this, I'm going to do a table. This is tabular. So we're going to let this be u and this dv. And so what do we put in this column? The x cubed, right? Because we put polynomials before exponential in Lipit. So then we put e to the negative x here. And then we differentiate. So this is 3x squared, 6x, 6, and then 0. And then we integrate this. So these signs are going to flip-flop. So this is going to be negative e to the negative x, e to the negative x, negative e to the negative x, e to the negative x. And then I make this plus, minus, plus, minus, plus. And then we multiply down here.
So they end up all the same.
Sorry?
No.
Yes, they're all negative. Interesting. Okay, so now we're going to say that this is equal to, since this is improper, we have to say the limit as b goes to infinity of the integral from 1 to b of x cubed e to the negative x dx. But we've done all the hard work over here. So we're going to say this, I'm going to scoot over here because this is a lot of terms. The limit as b goes to infinity of, well, that's going to be what? X negative x cubed over e to x. I'm just going to put it in, right? I'm going to make the exponents positive. Okay, minus 3x squared over e to the x. Minus 6x over e to the x. I could factor that e to the x out. I'm feeling it now, right? Minus 6 over e to the x, such that we're going from 1 to b. All right, so this equals the limit as b goes to infinity of negative b cubed over e to the x minus 3b squared over e to the x. Oh, e to the b, I'm sorry, e to the b. E to the b minus 6b over e to the b minus 6 over e to the b minus, now I'm going to put 1 in everything, right? So what happens when we plug 1 in? We get 1, because they're all over e to the first, right? Do you agree they're all over e? And then I'm going to put 1 in here. So we get 1 minus 3 is negative 4, right? Negative 4 minus 6 is negative 10. You guys are testing me, right? Minus 16. Nobody's screaming that I'm wrong, so that's a good sign? Yes? Okay. Now let's talk about, do we need to do L'Hopital's for b cubed over e to the b? That's infinity over infinity, right? Negative infinity over negative, right? Which one's going to go away? This one's going to go away. So this goes to 0, this goes to 0, this goes to 0, and this goes to 0. Everybody agree? So all of this madness goes to 0, and I'm left with 16 over e. Therefore, I put since, but therefore, what happens to this integral? it converges. And then by the integral test, so too does this. Right? They either both converge or they both diverge, kind of like the limit comparison test. So how do I know when I'm going to do the integral test? When I look at it and I think I can integrate it, right? You need me to make it closer? Yes, sir? Because it's got an infinity up here. He's going to make me have a heart attack again. It's okay. At least you know where the infinity button is on your calculator. Oh, don't say that. I know you do, right? It's improper because I can't have an infinity on my upper limit of integration because it's not a definite integral because I don't have a definite starting point and a definite ending point. It's not definite. It's improper. Okay. Yeah.
Are we gonna have a calculation on this test?
I have one page.
Can we look at the 9-3 homework?
I'm here to serve. This is from test 2020, right?
Okay. There were 4 problems on there today. We don't have to do all of them at once, but if you want to do all of them.
This is 2020.
I can do them in order, but if we're doing questions.
Yeah.
Okay.
9-4.
My first question was number 19.
Number 19. The instructions are find the radius of convergence. So I don't have to check the endpoints. That's the beauty of that statement. So we're going to say the sum from n equals.
Wait, I don't know. Oh, we're doing 9-3, not 9. Oh, yeah.
You said 9-4? No?
Maybe I did. I meant 9-3.
Okay, all right.
I'm
No, that's all right. No problem. I can adjust. This is me adjusting.
sorry.
My ears could not be working too. That happens a lot. I have only one functioning one, so here we go. Number 19.
Looks like my handwriting.
Suppose P3 of x is equal to x minus x cubed over 6. This looks like it's a sign problem. To approximate sine of 0.5. Give an error of the approximation based on the alternating series error bound. Okay, so the alternating series error bound. Okay, so what is sine x equal? Sine x equals x minus x cubed over 3 factorial, right? Plus x to the 5th over 5 factorial minus ... and so on, right? So this P3 means I'm just using this much of it. Agreed?
Right.
The alternating series error bound says, since this is an alternating series, clearly it is, I can use the very first term I threw in the trash to approximate my error. So I can say the error, or absolute value of the error, is going to be less than, I'm going to take x, using this term, I'm going to say x to the 5th over 5 factorial, such that x equals 1/2. So we just plug 1/2 in. So this is going to be 1/2 to the 5th over 5 factorial, which is equal to 1 over 32 times 5 factorial. Now 5 factorial, I think, is at 120.
Yes.
Okay. So 120.
Wait.
120 times 32. I don't, 0, 4, 2, 0, 6, 3. Is that right? 0, 4, 2, 0, 6, 3. So this is equal to 1 over 3840. And I don't know what that decimal is.
So all it is, so alternating series is just the first term.
Yeah, I thought I did that with you guys. Did I?
You did, I'm just like clarifying in my head, and then,
I'm about to do Lagrange right now.
okay, and there's one other type, right?
So you'd have exact by doing the f of x. I could do sine of 0.5 minus what this is at 1/2. That would be the
Okay.
exact. And then you can do, if you have a geometric series, you can do the truncation error. But this is not geometric.
Okay, and so Lagrange is the one with the M?
Yep.
Okay,
So this is Lagrange error bound. Now my answer is going to be different than the book.
okay.
And you have to be okay with that because I'm right. Okay, so that means what polynomial this is 3, right? So Lagrange says the 3rd degree remainder, right? I'm using 3 here, even though I'm going to use the 4th here. Excuse me, is less than or equal to absolute value of the 4th derivative evaluated at some c times, what's this, the center is 0, right?
Yes.
So it's going to be x minus 0 to the n to the 4th, because that's the n plus 1th, over 4 factorial, right? Such that x equals 1/2, right? Because we know that that's how far away we are from the center. All right, now I need to know, this is m. This is the maximum of the 4th derivative. Now, does this sine function have any amplitude? The answer is no. So it's 1. Okay, so cosine and sine are always going to be 1 because unless you have some kind of amplitude in front, like if you had something in here and you were every time you took the derivative, you were multiplying it by something, it changes its amplitude, therefore it changes its maximum.
What would you do if it was, if it ended up being a function that didn't have a max? Or will it always have a max?
In that, yes, it will have a max.
Okay.
Well, if not, you just use whatever the constant value is. Because it would be like if I had a function that didn't have a maximum, that would be something that looked like that.
Or,
And I would just use that.
like, I meant it increased on.
Then you'd use the one at the end point where it was positive.
The end point, which would be 0.5.
Yeah,
Oh, okay.
But we're already going to take 0.5 into account here.
Okay.
All right. So we're going to put, what we're going to do here is we're going to put a 1 here. And then we're going to put 1/2 to the 4th over 4 factorial, which this equals 1 over 16, right? 1 over 16. 2 to the 4th is 16. So this is 16 times 4 factorial, which is equal to 1 over 16 times 24. Good night. I have to multiply that. Here we go. 16.
You can't just leave it like.
You can. But I want to compare these two numbers.
Okay.
What is that? 4, 2, 14, 4, 2. So that's 4, 8, 384. Is that 384? 1 384?
Yeah.
1 over 384. So somebody have a calculator, they can do that division for me?
Well, it's like, it's just.
It's a factor of 10.
Yeah.
So I know this is smaller, right?
Mhm.
But I don't know what the exact, what I want to know is I want to know what the exact is and make sure that this is bigger.
Oh.
Do you know what I'm saying?
Mhm.
So this is an upper bound for the error.
Whatever 384.
And I want to know what the sine of absolute value, the sine of, I'll put exact here. of course, people can't see. Exact error is going to be absolute value of sine of 0.5, make sure you're in radians, minus P3 of 0.5.
Oh, okay, so the next.
So the alternating series error bound is really easy. You just use the one you threw in the, right? We just threw this one in the trash.
So there's 3 errors total that you could do, okay.
But if your series isn't, well, and why say that? Could you theoretically, even if it wasn't alternating, could you say you're approximating using the first one you threw in the trash? Sure, if they're asking for an approximation and they don't tell you which method to use. Yes, you could say that. Using the first discarded term. But they'll say, well,
I have the answer.
oh, what is the error exact?
So is it okay if I teach you in scientific notation? Do you want me to?
Oh, sure.
Okay, so it's 2.589 times 10 to the negative 4.
Okay. And then what is our upper bound? Did you do that? Is it 1 over 384?
0.0026.
Is that bigger than this? So this is an upper bound. It's saying the error is going to be less than that. And is our error later less than that?
This more.
I bet you this one's close to, this is probably really close to the exact error. Why don't you do that and see what that one is? Yes.
What's like the variable thing? Like, it's like m times.
Yeah. Okay. So
I just want to write it down. Yeah, it's 0.0002 off. So.
right, but it's very close. Is that what you mean? A is the center and m is the max of the n plus 1th derivative. And we say if I'm using a 3rd degree polynomial, like this one, I'm using a 3rd degree polynomial, then this is 3. So this becomes 4. Right? So this is a 3rd degree polynomial.
I see.
So the remainder for the 3rd degree polynomial is the n plus 1th. Even if I know that this next term is 0, don't I? The 4th degree term is 0? The answer is yes, right? You still use the next one because it's not 0 at 1/2. And that's the key to it all there.
So if you were given like a range instead of at 1/2, would you just plug it into the very end of the range?
Yes. Because the error is always worse at the edges.
Okay.
That wouldn't be very nice of them, but yes, that's all you do. So on 21, what are you going to do? You're approximating cosine now at 1/2. And then you're going to use, for the alternating series error bound, you're going to use what? X to the 4th over 4 factorial, right? And then for the Lagrange error bound, you're going to use, does that cosine have a coefficient or amplitude? No. So you're going to use 1 as your m, and then you're going to go to the 3rd derivative, which is just, I don't even know, but it doesn't matter. The amplitude's 1, right? And then you're going to use 1/2 to the 3rd, because your center is still 0. If your center was something other than 0, you'd have to put a, this would be like, let's say your center was 1 and you wanted an approximation for 1.5. What would you do? 1.5 minus 1. So you're like, this is saying how far you are away from your center, basically. All right. So I think you can do 21 now. It's pretty, but it's going to be different. The alternating series error bound will be the same in the book. But remember, the answer in this book will be incorrect for 21. You just use the 4th or the 3rd degree instead of the 4th.
Okay, so it would be n plus 1, so would it be? Oh, okay, so it'd be x to the third.
over 3 factorial, yeah. Yeah, so it's gonna be different than the answer book. And then you're gonna do, okay, so that you would do the second, this doesn't alternate here. The approximation can be used when x is small. Estimate the maximum error graphically. So that, what does that mean? That wants you to find the square root of 1 plus 01 and compare it to what happens when you plug in 0.01 in the calculator. You know what I mean? You know what I'm saying?
Wait, where?
On 23.
Oh, yeah. So
Number 23, you have the square root of 1 plus x is approximately 1 plus x over 2, right? And it wants you to compare, well, and they gave you the absolute value of x is less than 0.01, right? So you're going to have a range, negative 0.01. That's close, right? I think that's right. Yeah. So what they want you to do is say, okay, well, what is 1.01? And how is that different than 1 plus 0.01 over 2? Because that's the exact error. And they want you to do it graphically. So you could graph this one, and you could graph this one, and you could say let x equal 0.01, and or you could just graph this and see what the difference is between the two of them. I think that's what it's asking you for.
Okay. I was wondering, back on like 19, why would the alternate series error bound be more specific than the Lagrange error bound if you're like skipping one for the alternate series?
Because this is going to be smaller because it's one more term away. Is that what you're asking me?
Okay.
And this is just this is like the piece of the fourth or of the fourth derivative, right? That's different than 0 that this one doesn't take into account. You know what I'm saying? I mean, although it's taking this into account, but it's going to be smaller because the biggest part of the error is always. So let's do let's say we're doing it at 1, right? Or let's say I have the sum as n equal 1 to infinity of x to the n, right? And I'm gonna let x. No, I don't want to do that one. I want to do negative 1 to the n 1/2 to the n minus 1. And what do we get? 1 minus 1/2 plus 1/4, right? Plus or minus 1/8 plus 1/16 and minus 1 over 32. So if I only use this much of it, and this is my error, this is the biggest number by a lot. This one is way smaller. I mean, I don't even, what is 1 over 8 decimally? I don't know.
0.125.
0.125. And what is this one? 1/2 of that? 0.0? Just let's have it.
-625.
We should have trusted you. And this one is going to be,
0.03125.
there we go. You found it. Okay, so is this bigger by a lot? I mean, I think it is, right? And so so if I'm not using this one, I'm going to use this one. That's even smaller. I don't know if it's the absolute value of the magnitude. But there's some part of the function that's not 0, between 0 and 1/2 of that fourth derivative. Because how do we create the cosine? How do we create the cosine polynomial? We evaluate it at 0. We're not evaluating it at 1/2. Right. Does that, I don't know if that, right? Because if we were creating it at 1/2, there wouldn't be any error
Yeah.
because it converges for all real numbers. But these were created at x equals 0. And so there's a contribution. I mean, you have y equals, was it cosine? No, it was sine. I'm sorry. I'm talking about cosine. This is sine. Y prime is cosine. Y double prime is negative sine. Y triple prime is equal to negative cosine. And y fourth derivative is equal to negative sine. No, positive sine.
Okay, wait, I think I got it.
You know, okay, so what am I going to do to create this polynomial? I'm doing y of 0, y of 0, y prime of 0, right? And so we used the fourth, didn't we? We used the fourth. This derivative, although the sign is 0, the sign of 1/2 is not 0. So there is some contribution to the error because of that. And that's what Lagrange takes into account, that the alternating series error bound does not. Yeah.
Will you always tell us which area you want us to use?
Sometimes they will and sometimes they won't. So you get to choose. So that's okay. And I'm going to choose the easier one. I would do the alternating series error bound or choose the very next term and say that's what I was doing. And if it tells you to use, oftentimes it'll tell you to use Lagrange. But it doesn't always. So that means if it doesn't, it's your choice. Okay? I perhaps will be telling you tomorrow. Yeah, I won't make it a mystery, I don't think, because I wrote it already. Right? Pardon? Your pencil can't stop moving. So you have to know what you're doing. Okay, so when you have to know what you're doing, tell me the things that you know how to do, right away that you have to do.
Well, we already did the normalization.
Okay, yeah, well, I copied and pasted the chart from your creating series from other series. That's page 1.
So you're just getting.
Like, it's given to us. It is given to us.
E to the x, blah, 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 IOC.
So we have to be able to use those to create
Yes.
other ones.
Yes. Okay, so yeah, so you're going to have to use ones created by other ones. Yes. Yes. Because of course you'll have them. Hopefully they're up here and you're going to, well, the problem is I want you to look at something like on some of these from the series thing. I want you to be able to look at something and goes, oh, that looks like cosine. Or some variation of cosine. Do you know, like power series. There's one on here. I was like, oh yeah. Okay, here we go. I don't know what page this one is, but it says the third degree. I'll zoom in. The third degree Taylor polynomial of x e to the x. What do you have to do for that, right? I mean, you got to know what to do. You take the e to the x that you know and you multiply by x, right? That's all you do. This one is secant x, and then if you don't know the one for secant, when I don't, I guess you could put 1 over the cosine, but that would be awkward, right? Because then you have your polynomial thing in the bottom. So what do? You take the derivatives until they want the second degree. So they don't want you to go very far, do they? So you just have to go function first, second derivative, right? And then evaluate. I swear there was a multiple, okay. Like here's one. This one says the graph of the function represented by the Maclaurin series, x cubed over 3 plus x to the 5th over 5 plus, that's inverse tangent. Well, it's no factorial, right? So if there's no factorial, it has to be inverse tan, okay? So but I want you to know that it's either sine or inverse tan is a good thing. So knowing what that is is imperative because, you know, it says find out where they intersect, where e to the negative x intersects this. So what do? You have to, in your calculator, put inverse tan in y1 and this in y2 and see where they intersect. But you have to know that that's what? Inverse tan. That's why I want you to memorize those. So you go, oh yeah, inverse tan. When does that equal e to the negative x? Let's see. Takes you less than a minute, right? Because we have 2 minutes a question on the multiple choice. Well, in the calculator section, you have 3, but yeah.
So the way you wrote it on there, like to solve for the intersect, can you just say solve and then put the two equations equal solve for x?
Yes, you could. But you know what happens is if it's periodic, you get that little ampersand, you know, the little at symbol. And so
So would you just graph?
I just grab it. Yeah.
Okay.
If there's a trig function involved, although in arctan just looks like, you know, an e to the negative, it only intersects once. So that's good. But,
Okay.
you know, and so stuff like that. And like this one, this says a series expansion. Oops, I'm sorry. Series expansion of x minus sine x over x squared. So what do? You take x and you subtract out the sine that you should know, right? Without having to go back. And that's how quick I need you to be. Okay. And like this one says, this is the Taylor series about 0 for which of the following functions? Well, this has got a factorial on the bottom and it's not x to the n, it's x to the n plus 2, which means I did what to it? The x's. I multiplied by x squared. Do you see what I mean? And then it's alternating, so you put in a negative x. So little stuff like that is going to help you. That's why I try to make you memorize those, because I think that helps. Makes you quicker. So you can spend time on the more difficult ones. All right.
Like the tests.
No, I think there's some easy ones on there. Let's see, I've got the 2020. Let's look at the 2020. I'm sorry, the printer has lots of line issues today. I don't know what's going on with the printer, but
Oh, and on this 2019 test, I think there's one page that isn't, I don't think the answer key is for it. Maybe it is, I just couldn't find it, but it was.
could be
like-
in the end. Is it at the end?
I think so. It was, mine printed out of order anyway, so it was kind of hard to go back and forth, but it's the part where it's calculator section. I don't think I can find it. Yes, that. I didn't find it on Moodle. I mean, I can check one more time, but
Well, it might not be on there.
2019.
Okay, so this one I gave you a function, right?
Mm-hmm.
And how do you find a Taylor polynomial? Do you know how to do that on your calculator?
Yeah.
That's what you do.
I think I got it right. I just was kind of trying to double check. But.
So you put the first degree here, first degree, and whatever degree, whatever, you know,
And then second.
Yeah.
And like you add them.
yeah, you add the terms as you go. Yeah, but you know, the first one's I don't know how many terms it was, but I'd have to find my key, but that's what you do. And then this one here,
And the error is pretty easy.
yes, it's very easy. Yeah. And then this one here, you just take the highest degree and then you do Lagrange, which means you have to have the n plus 1th derivative, right?
And you plug it in at 0.75.
Yes.
Okay.
That's all you do. That's all you do, Jim. But let's look at the 2019. Obviously, page 1 is done. You already did that.
Mhm.
There's going to be 6 multiple choice questions. Well, this one had 7, but I only have 6 on it. Okay. You're going to find this question on the 2019 and the 2020. And was it on the 2017?
With the x equals.
Yes. That's a signal.
What number is that?
8.
It's never said on 2020.
What?
And
This was on the 2019 and it's on the 2017. Yes, look at that. It's there, number 7.
Miss Muller,
Yeah.
on both of your keys, I think, on your nth term, shouldn't it be like f to the nth derivative of 0 or a or whatever over n factorial times?
Did I
over
leave
x
off
to the n?
yes, I do
Okay.
that, right? I always leave them off. That
You
very
did on
last
the
one.
summation.
What?
You did it right on the. like, the
Yes,
summation.
right. I always, you know what? I don't know what happens to my brain as I
Yeah,
keep
it's
going. I'm
on-
really good until the very end.
On both keys.
It's
too.
amazing, isn't it?
Yeah.
Okay, so that's my weakness. We know what my weakness is. You guys won't have that weakness.
Have you posted these answers to the-
Yes, I have.
Um,
And okay, it's 2 documents because the first document is 22 pages.
oh,
And then the work associated with it is in the other document because it's 12 pages.
And then I had one more homework question. It was on the 9-3. It was 33. It was only part D, but I don't know if we can do part B without doing the rest.
Part D, okay, so that's going to be A minus the what's the series we know? We know the natural log of
1 plus X.
1 plus X.
Because the series in part C was, yeah.
This was an AP question, you know.
Oh.
Mhm. Okay, so what is the series in part C? What is the natural log of 1 plus X squared?
It's X squared minus 1/2 X to the 4th plus 1/3 X to the 6th.
Okay,
minus-
hold on. Plus X
Plus
to,
X to the 6th over 3.
oh, right, plus or minus X to the 8th over
Yeah.
4.
Right.
Plus plus -1 to the, are we starting it at 1 or are we starting it at, did you say that's all right? If I started at n equals 1?
Right.
I think we're okay, right? Okay, so, find a rational number A such that, okay, so a rational number A, so ln of, hold on a minute. Ln of 1 plus X, right, is equal to, if I wanted to break ln of 5/4 into something, I could say that this is the natural log of 1 plus 1/4. Would you agree with that?
Right.
So that would be at X equals 1/4, right? Because this would be 1 plus X. So we could say that X equals 1/4, couldn't we? So we wanted to say the some number, which is going to be some combination of, it's because it looks like this right here, absolute value of A, minus natural log of 5/4 looks kind of to me like error. Does it look like error? I mean, doesn't it kind of, because it's absolute value and it looks like I have ln of something, and we've been dealing with this, ln of something, and ln of 5/4 is 1 plus 1/4, right? So we're going to try to figure out what polynomial that I'm going to use here. I'm just going to call this polynomial of n, I don't know, of 1/4.
Why would you not have it be ln, the equation where we found what X was, why would you not have it be ln of 1 plus X squared, since that's what we already had? And then solve with X for that. And make
Well,
X
okay, what would,
1/2.
and when we make X squared 1/2, we could do that too. We could do that too.
Okay, I'm just trying to follow,
Yep,
I would.
we could do
look at
that too.
this-
I'm just doing 1 plus X, but we could do, if we wanted this to be X squared, sure,
Okay.
we could do that and make X equal 1/2, sure. We could do that. Okay, so then we need a polynomial evaluated at 1/2 such that was less than 1/100. Okay,
So is it ln of 1 plus 1/2 squared?
yes. But this is not squared,
Right.
right? That is not squared.
Okay.
But this, yeah, that's squared.
Okay.
So then I got to figure out what happens if I want polynomial of some sort here. So I'm going to say p of 1/2 is equal to what? We get 1/2 squared, which is 1/4, right?
Mhm.
Minus, this is going to be 1/16 times 2. Because if I put 1/2 in here.
Mhm.
So what is that? If I found a common denominator here, that's, I don't think it's going to be enough. Plus 1, to 6, 2 to the 6th is 64 over 3. That's probably too big, right? Well, anyway, well, these are what we're going to work with here. So what's 1/4 minus 1/32 plus, what is that? 192?
Yes.
I just did that in public and nobody was like, ooh, good job, Mrs. Miller.
Good job.
You know what I'm saying? Holy cow, right? My brain is firing today. So I got to multiply this by, this is 64 times 3. So that's going to be 32 times 6. 6? So this is 6 over 192 plus 192 minus, and this is going to be, this is 4 cubed. So that's going to be 148. You got to check me on that. 4 times, this is 4
Yeah,
times,
that's right.
oh man, oh man, sign me up now for, so what is 48 minus 6? That's 42, right? Plus 1 is 43 over 192. Is that less than 1/100? I think it is.
Wait, no, it can't be. Can it? That reduces to like around a fourth-ish.
Does it reduce?
I mean, like if you were to think about it,
4 over 200?
like 50
1 over 50? We have to do
200.
one more? That's going to make my brain hurt now. Minus,
Wait, isn't that what we're trying to get? Is get it less than? Because that's about a quarter-ish. If you do like 50 over 200, right?
I want this to be bigger.
Yeah. Okay. So we have to go a good bit more. It was like 43 over. Yeah, it's like 0.23, like 0.223. So it's
So we got to go one more?
at least, yeah.
Okay, so 2 to the 8th is 256?
Yes.
It's going to fail after this, minus, but I'm subtracting. Okay, so that's going to be
Times 4 is.
256 times 4 is 4, 2, 1024.
Yeah.
So I got to get all of these in the same denominator. My head's hurting.
Yeah. That's not right.
Okay, well, the good news is that I'm not going to change the 1024. We're stuck with that.
You can't get 192 to go into that, can you? So when you have to multiply, because 192 doesn't go into 1024.
I don't know. You have the calculator.
Okay, wait, let me see if.
So what you should do is go 1/4 minus
Oh,
1.
if you multiply one, so it should be 3072 because 1024 times 3, 192 goes into it.
Okay.
So then, okay, so
Just add with these. Add these up with your calculator,
we'll have a calculator for that, right? Like,
or you can leave it like this. You just have to know it's
oh, okay.
less than
so-
1/100. Oh,
It's not, how is it ever gonna get to it? Cause
Okay.
that's just around 0.22.
I had a thought that maybe we should, this difference has to be that. Right?
Well, that's probably what it is.
Yeah,
I was like, cause then we'll never get to less than.
no, yeah.
Okay, that makes more sense.
Oh, they did it even.
What did they do? They did.
Oh, okay, yeah. So they say the first term of the series that's less than is the sixth one. And they say, let A equal 7/32. The first term of the series that is less than 1/100 is 1/3. Did they say?
Why is
Do
that
you
the
see?
sixth?
Wait, hold on a minute. Okay. Here I am trying to find the exact error, right?
Mhm.
And I'm approximating. We're approximating. So the first term I'm going to throw in the trash is what I'm going to use as my approximate to be less than 1/100. Okay?
Kind of rational. How do you like know that though from reading the question?
Because it doesn't say the word Lagrange or it doesn't say exact error anywhere, does it?
Okay.
It's an approximation. Okay? So what is what is it when we do this one? We do the first two. That's going to be 8 30-seconds.
You want decimal? Or?
No, over 7 30-seconds, right?
Oh.
Which is equal to 1/32, right? No, wait, try again. I did it backwards. This is 1 and this is 7, right?
Mhm.
And so what they're saying is 7/32 minus natural log of 1 plus 1/2 squared less than 1/100.
Okay. I understand the work for it. I'm just like, my problem is reading it and thinking to do that. You know what I mean?
Right, I do. And this was part D on one of the AP exams, and I imagine that nobody ever got that, but I had to bet. So what does this, what's the difference between, or what is this? Because that's the first one we threw in the trash.
Mhm. So.
If we used the first two, we get 7/32, don't we?
Mhm.
If we use the polynomial degree 2, we this, or the degree 4, right? If we use this, the number we get is 7/32. Okay, so 7/32, what would I be throwing in the trash? Because this is alternating, is it not? I'd be throwing this in the trash. Is 1/192 less than 1/100?
Yeah.
Yes. This is the alternating Sears error bound.
Oh, and that's just another error. Okay.
That's what, I misread it myself, because right here, the question is saying, use the series found in part C to find a rational number A such that this thing, whatever you're going to use for your polynomial, minus the natural log of 5/4 is less than 100, okay? So it's asking you for the error indirectly to be less than 1/100. Well, so you write them all out just like we did. I mean, we did the right thing by writing them all out. But if we use these two, this one is 1/100. This one's less than 1/100. That's what it's asking you.
Okay.
Right? So this would be, I'm sorry for the messy on my paper, but this would be the second polynomial evaluated at 1/2 minus the natural log of the 1 plus 1/2 quantity squared would be less than 100, 1/100, because this is 7/32. And what's the first term we threw away, which was 1/192. That's what that is. And it was weirdly worded. It's absolutely very strange. And we could look up the scoring guidelines.
Cause I got part A through C.
No,
not through
right, and
that.
that's what happens, is they sometimes do weird stuff like that and throw everybody off. So that's what's wording the problem. It says, I don't know what exam this was on. Use the series found in part C to find A. Such that, let's see what comes up. Huh, 2008. I don't know.
Form B.
Form B, but that's AB. Oh, let's see. Let's
Yeah,
see.
it says BC.
Wow, there it is. Imagine that. All I had to do was type the question.
Is it to the percentage that got each part right?
I can figure that out. Yeah, hang on. Okay, so what's the good news? Number one, if you use x equals 1/2, which we were doing, right, you get a point.
Okay.
You get a value for figuring out that the first two, we wrote the first two down, right? That's good. And then you just have to use the alternating series area bound. And that's what my mistake was. That I was thinking, oh yeah, this is error. I don't have to be exact. I was trying to find 1/100, you know?
Yeah.
And, okay. All right. So let's see what the percentages are, if they have any. No, I'd have to look at the other stuff, but I bet you they missed that a lot. They probably averaged on this question, who knows? Let me see, what is it, 2008? Question 6?
Yeah.
2008 BC Form B question 6. What do I want to do? 6. I want to do statistics.
AP 08 statistics from Form B. It's like that, right there.
Yeah, I know, but I don't know if that's going to have. No, it's not going to have that. There are some documents that they have the statistics on, you know. And I
Maybe
thought
like
first,
percentage
or
score percentage.
what was it? What did we say? Average score.
Average points scored.
That's AB. I can look it up
Okay.
because I probably have it at home in a book somewhere.
Which one of our units has the most questions on?
I want to say this one.
Here.
It does. Look at the top of
It has, oh yeah, it does.
AP exam readings. So.
at the top and the
Oh yeah.
it's 20. This is
Integration and
20%.
Accumulation is 17 to 20%. So the one that we.
Yes, ma'am.
No, it's just regular integration is like 20.
Okay, so what are you going to do here? You're going to,
And then
what's G?
This is.
It's this, what you came up with, right?
20%.
Yeah.
So you're going to write,
Actually, the
you just write x squared minus x to the 6th over 6 minus, what's G? Write that. X squared minus x to the 6th, 6 plus
Oh.
x to the 10th over 120, right? And then I go minus dot, 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 because that's enough to see probably all over x to the 10th. And then you cross off the things, right? This goes away, this goes away. And this is a plus, so this one goes away. And then this flips all the signs, right? So the limit as x goes to 0 of, so what do we get here? X to the negative x to the 10th over what, 120
Over 61, right?
over x to the 10th. Now this is plus some more, right?
That's true. You could just
Yeah.
get like
Oh, x to the 14 over, what does that say, 20, 40?
Yeah, I wasn't sure.
And then so, or 10 to the x to the 10th, I'm sorry. X to the 10th, so you're gonna cancel these and your answer is 1, -1 over 20, because these are all gonna go to 0. Right? If you were to reduce all of them by x to the 10th, this is 1. And so your answer is gonna be -1 over 20.
It's like a 36.
Do you see it?
Yeah. And then I just the whole like
And then you just
integrating.
integrate this. Just integrate this. You're gonna put, okay, you can go, you do this, add t squared minus t to the 6th over 6 plus t to the 10th over 120 plus dot, right, dt. You can do that. Just raise the power 1, divide by it.
Oh my gosh.
Right?
But it's with the t. Does it matter?
Right, well, that says g of t. Well, you have g of x. You just put a t where the x is. And so you're going to say, what is this? T cubed over 3 minus t to the 7th over 42 plus t to the 11th over, I don't know what 11 times 120 is. Set plus dot such that you're going from 0 to x and you plug in x and then you plug in 0. Right? And then you can do the same thing by figuring out what that is. You can just put that
So like
on.
I'm still gonna have to email someone.
And this would be
What would the spreadsheet? Because
x
their
to the
friend
2n
sent
plus
them the link
2
to the Google form and then the-
over 2n plus 2, right? You times this, if you find the answer, that's all you do.
They're a pair that's playing, so I have to
And
like
then you just,
email their VT emails, their assignment.
I thought you got upset.
then if you use the first two terms, then you're gonna use this one here.
Real Catherine.
And you just plug 1 into that, and that's gonna be less than that.
Martinez, though.
It's as simple as
I was
that.
gonna say, I'm-
It's a lot of words, I know.
And then this whole back page. Did you do this problem?
I didn't, but we can, we have time to do that one. Let's do that.
I'm down to do that.
Okay.
Can I just ask you something quick?
Yeah.
So I know we talked about this, and this too was on 2020 and 2019.
No, it's
Okay.
really.
No, nobody's.
And then,
Okay, you can't do the nth term on this.
okay, that's
That,
why,
that was a, question from Ron Miller. So I didn't,
and then do we need radius or convergence too, or no?
well, you can't. Yeah, you just can't.
So we just leave it as like that, and then I just put plus dot dot dot?
Yeah.
Okay.
Because, I wanted to challenge Ron and see what he could do. And it actually did stump him.
So can you actually not do it?
No, you can't. But you know, he could work my test 3 or 4 times,
So that's the top right now.
all right? And drive me crazy.
And look, this is the most thing to them. So first person.
All right, let me, get my calculator and we're gonna do this one. Is that all right?
Like,
Yes?
Ashton Phelps. Regan Dowd.
Hang on. So, and then with bias.
Yeah, it should be like over 4,000.
What?
The winners right now get over.
That was so close. Whoever's
For
winning
what?
Assassin is
I'm
getting
sorry.
a scholarship. For this, you said you can't.
Thank you. Yes, I was very proud of that.
Really?
And then I was doing comps of the week, and I like I was like gonna make a meme of the money and send it to people, and he was like top new bottom text, and I was like, oh, okay. But the so what were you saying, like making a spreadsheet? Like so, and then I would even ask me, no, I would have each group have their own spreadsheet and have like every week I would add their new assignment to it, and only they would.
I mean,
see it.
Sammy, just do like, literally just do whatever's easier. It's not really up to us. You know?
Right?
No.
I'm not being funny.
You know what I said.
Yeah, no, I have my own, you know what's really nice? So like, you know how Javier was saying he's like gonna use a graphics like that? Literally in Google Sheets, you can highlight all the names and click randomize, and that's it.
Really?
Yeah, so like, everyone's assignments are completely random, some are really fun to do.
what does yours say?
What does that mean?
3 halves or what does yours say?
No, it's just like seeing like if somebody.
This problem, what does yours say?
So we get someone they don't know at all, like it's just fun. I just look at it.
Could I?
No.
Can you tell me
Caller, can you do
Can I do what? I'm sorry?
number 71 on 5-5?
Yeah, just give me a second. Oh, so
Okay.
you say 3 halves?
Where?
Part E. Is yours say 5, 6?
Yeah.
Okay.
Yeah.
Okay. I was, because I had another version where it was a different number. That's why I was asking.
Is that the 2020 or 2019 one?
I think this is 2020. Is that the one you want me to do?
Yeah, it's the same problem.
All right, I'm doing this one from the 2020, and then I'll do the one you just asked about, okay? The 9-5, number 71, is that right?
Yeah.
Okay. Okay, so this one says the graph of arctangent is shown with the first 4 of its Maclaurin polynomials. Identify each polynomial on the graph by labeling them A, B, blah, 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 and list the polynomials. Okay, so now arctan, you guys know, right?
Inverse tan.
It's inverse tan. But let's pretend you didn't, and this is the calculator section. How do we get our calculator to create one? We have to go F3, we go up to number 9, which is Taylor. Do you see it?
Yeah.
Press enter. And then I'm going to go inverse tangent of x, comma, and I don't know how many I'm going to do. Let's do 7.
You do X.
Oh, we have to do x first. Yeah, I'm sorry. I was just excited about how many I was going to do. All right. Yeah, you have to put an x first. Yes, absolutely. Okay. All right. So I'm going to have my calculator kick them out here. All right. So do you see this is degree 1? X is degree 1. So you would say P 1 of x is equal to x. Everybody agree that that's the first degree Taylor polynomial? Yes?
Yeah.
And then P sub 2 is going to be, well, do I have a 2? I don't, do I?
No.
So I'm going to say P sub 3. Now, can you tell me on this graph which one is x?
Yes.
Y equals X.
This is A right here, isn't it? That's what I wanted them to do, is label that one, okay? All right, so then the next one's going to be x minus x cubed over 3. There is no factorial, right? And that one's going to be this one. So that's B. All right, and then the P, this is 3. P sub 5, right, that is going to be x minus x cubed over 3 plus x to the 5th over 5. So that's the 5th degree. Oh, wait, this is, no, this is not B, is it?
B is the one that's.
It's upside down.
Yeah. The bottom, it's like the bottom right line, right?
It's going to be like this one.
Yeah.
I'm sorry, the end behavior is negative, right? I'm sorry, I missed that. Then this one's going to be this one, right? This one's going to be C because it's opening up. All right, then the 7th degree is x minus x cubed, x third plus x to the 5th over 5 minus x to the 7th over 7. Agreed? And then this says find the actual error. So we're going to say f of 5/6, or can I say arctan of 5/6? Inverse tangent of 5/6. Oh, does it matter if I do f first or not? With the absolute value bars, does it matter? Do you care if I already wrote inverse tangent first? And then I'm going to go p sub 1 of x, or 5/6. Is approximately. And then what are we going to do? You got 2 ways to go here. I'm going to go to y equals, and I'm going to type in x, and then in the next one, I'm going to type in x minus x to the 3rd over 3. And then the next one I'm going to copy this, Control C for copy, and then I'm going to go Control P for paste. And then I'm going to put at the end what? Plus x to the 5th divided by 5. And then I'm going to go Control C, copy. And I'm going to Control P, paste. Right? And then I'm going to go and add the last term, which is negative x to the 7th over 7, right? All right, so I have in Y1, I have this one, in Y2, Y3, Y4. Got it? It's the only, D is going to be x to the 7th, which will be this one. Because that's negative end behavior. All right, so where did I put Y1? What's in Y1? I'm sorry? X. All right, so I'm going to go to the home screen. I'm going to clear this out, and I'm going to put absolute values. So second, math, num, abs, and I'm going to say arctan, which is inverse tangent of 5 divided by 6, minus y1 of what? 5 divided by 6. Close, close. And I'm going to diamond approximate. And what do we get? 0.13. Is that 9? 139, yes? All right, now what am I going to do on this one? Inverse tangent of 5 over 6 minus P2. Wait, they want the highest 3. Oh, no, for the first 3. So P3 of 5, 6. How do I do that? You guys are going to do this one really fast tomorrow, aren't you?
But you get 0.139.
Yeah. You're going to do this really fast because you're not going to have a lot of time. All right, and so where did I put the second one? I put it in Y2. And what do you get? 0.0543. Okay, and then absolute value of inverse tangent of 5 over 6 minus P4 of 5 over, no, P5, I'm sorry. 5 over 6, approximately. Where did I put the third one? I put it in Y3, diamond approximate, and that's going to be 0.0261. Those are pretty easy, yes?
Yes.
Okay. Now this says give an upper bound for the maximum error when using the highest degree above using the Lagrange error bound. Okay, so what's the highest degree polynomial here? 7th, okay? So if I'm using the 7th degree, I'm going to say Lagrange error bound of the 7th of what is the, I want it at 5/6, right? Because that's the outer limit. Such that was going to be less than, or I mean, less than, well, I need the maximum of which one? Not the 7th, but the 8th. So I'm just going to put that right there. And this is going to be, what's the center here? The center is 0. So this is going to be 5/6 minus 0 to the 8th over 8 factorial, right? So now I'm on a mission to find the 8th derivative of, yes. Now how do I do that with the calculator? F3, right? Differentiate inverse tangent of x, comma, 8.
So the left part, is that just saying Lagrange, or like what the left part in, it's like remainder 7, 5, I don't get what that part's supposed to be.
What part?
That's saying the error.
This is
less
the, this
than
is,
or
this
equal
is, this
to-
is the remainder using the 7th degree Taylor polynomial.
Okay.
The remainder is all the
everything after
rest,
that.
yes.
Okay.
It has to be less than or equal
Oh,
to,
yeah, because the remainder plus the polynomial is the real.
yes.
Okay, okay.
All right,
Did you, what power is that? 5, 6 minus 0, or what?
oh, to the 8th, I'm sorry, yes, it's 8th. Yes,
Are you solving for m in this or?
I haven't even, I've done everything but m.
Oh,
But what I did was I found the derivative, the 8th derivative of tangent. That's inverse tangent was right here. Okay. My calculator found, I have to have the maximum of the 8th derivative of this thing. That's, so I do on the calculator, right? Because I don't want to do that by hand, right? And so this is the 8th derivative. It's crazy.
yeah.
Okay, so I'm going to copy it. Controls or a diamond copy. I copied it. And then I'm gonna y equals, and I'm gonna put that in y5, control paste. There it is. And then I'm gonna deselect using F4 all of these. And now I'm gonna graph, and I'm gonna look at my window because my window is pretty good, right? It's looks like, well, I don't need X max that close. We're gonna say 2. And we'll say 2 here. Because I'm matching what I have here, right? I see the 2s here. So diamond graph. So I'm graphing the, what derivative? The 8th derivative.
Do you only graph Y5 or do you graph Y4?
I graphed only Y5.
No. How do you cancel it again?
Press on. Okay, so it looks like I have to have a bigger window. So diamond F2, what should we do? Negative.
Do you do 20?
Okay, I still need it bigger.
So you find the max of that and then plug it
Yep.
at the end.
Now, if let's look at the function itself. I'm going to go home and let's look at the function. What does it say here? It says negative, I'm going to hop off. Negative what? 4,320? Okay. And when X is 0, it's zeroed out, right? Well, that's negative and that's 1. So it's 0. That's 0, but okay. So I'm going to do such that here. Let's clear this out. We're going to go such that X equals 5 divided by 6. And what do we get? Negative 405. All right. So diamond window. Let's make this negative 500 to 500 and see what happens.
What was your X?
5/6.
Like your window? Was
Yeah.
5/6?
Okay. So what's going on is at zero, it's passing through 0. So it's down and coming back up again. It's really tight in there. And so on the outer edge, what did they say over here? It's 400 and what did we say?
Negative 405. Is that what
Yeah.
it was?
We want the absolute value of that. So we're going to say 405.564 times 5/6 to the 8th over 8 factorial.
Okay.
On Tuesdays, I don't have one that's that big.
Okay. That sounds good.
Yeah, it's not that big at all. But that's what you would do, okay?
Okay.
They had theirs on a different day. They had this and they had their,
Yeah, this says problem of the day. Did you?
yeah, I gave it as a problem of the day. Yeah.
Well, I'm gonna head out, but thank you.
Mhm. Welcome. So I know you don't feel satisfied, but so how do you find a max or a min if it's passing through 0? It has to be on the outer edge, right? It's either at 5/6 or it's at negative 5/6. Because that's the range that says absolute value of X is less than or equal to 5/6. So negative 5/6. It's not less than or equal to, yeah, it is. Right? And so you check it out at these two numbers to see if they're bigger than what's going on closer to the origin, right? Because what happens on this graph, and let's change our window a little bit here. I want to go from -1 to 1. It's gonna come down and then it's gonna come back up really close to here. And so at 5, 6, it's a negative number over here. You know? Well, let's see if we can find, and then there's another,
Alright.
Clear, you can also do this. You can say F2, wait, F3. F max. It'll tell you the max too. But that's what I would do. All right. I should have made this question not from the highest degree, maybe, right? Maybe I should have done a lower degree. That would have been better, maybe. So, I don't know. So, well, I hope it helped. I still owe somebody a question from my home, right? It was number 70. What was it? Number 71 from. You guys can go. You don't have to be polite. It's okay. It was 71 from what number?
5-5.
9-5?
Yeah.
I will. All right. You bet.
Have a good day.
You too.
Thank you.
Bye, Miss Moore.
Yep. Have a good one. All right. Number 71, you said, right?
Yeah.
Multiple choice says, which of the following gives a truncation error if the sum of 100 is used to approximate the sum? Okay. So if you use 100 terms, what's the first term you're throwing away?
101.
So you want the 101st term. Okay. So if I do this, the sum from n equal 1 to infinity of -1 to the n over 2 to the n. I'm just going to lay out a couple of the terms here first. When I let n equal 1, what's my first term? It's -1/2, right?
Yeah.
And if I let n equal 2, it's going to be +1/4. And if I want 100 terms, the first one I throw away is going to be the 101st, right? So what is the 100 a sub 101? Well, I'm going to plug in 101, right? So this would be -1 to the 101st, which is a negative number, right? Because it's odd. So it'd be -1 over 2 to the 101st,
Yes.
correct? Okay, and so what's r every time? Can you tell me?
-1/2.
R equals -1/2. And we have this wonderful formula here that says, I can say the sum from n equal 101 to infinity of my a sub 1, which is -1 over 2 to the 101. I'm sorry, this is 101. R is -1/2 to the n minus 1. So what happens when I put 101 in here? I get this number. This is 101. I can't even see it myself. Right? And I put 101 in here, I get what?
100.
100. Wow. Yeah, that's right. Okay, but oh, wait. I need this to be, what is a sub 1? A sub 1 is this. This is, I don't like that. Hang on a second. What I'm trying to do, not very successfully, is we go out to way out here and we get -1 over 2, 1 to the 101, right?
Yeah.
Minus, or plus, I'm sorry, 1 over 2 to the 202, 102, sorry. Right, do you agree with that?
Yes.
And then minus 1 over 2 to the 103 and so on, right? Do you agree?
Mhm.
So I know that the sum of a geometric series is equal to, if I, 101 forward, right? Or to infinity is going to be a sub 1 over 1 minus r, isn't it?
Yeah.
Well, a sub 1 is this for my new series. Do you agree? Because I'm taking all the first 100 and then I'm throwing these in the trash. So the truncation error is going to be geometric. So it's going to be negative 1 over 2 to the 101 over 1 minus a minus 1/2, because that's r. And so that's going to be negative 1 over 2 to the, this is 101. 2 to the 101 times, this is 3/2, right, on the bottom?
Yes.
So this is going to be 2/3. And so this is a 101. What am I doing? But what I'm doing is I'm subtracting the 2 already. So this is negative 1 over 3 times 2 to the 100. Is that a choice? You see it?
Why did it go to 100 instead of 100? Why did it go to 100 instead of 101?
Because this 2, I cancel one of them.
Oh, got it.
Yeah. And I don't know why I wasn't able to write the sum here. It's weird. I'm going to try to write it again because I'm not satisfied. We're going to start with n equal 101. And this is going to be negative 1 over 2 to the 101, because that a sub 1, right?
Mhm.
And then I want this to be negative 1/2 to the, I guess it's going to have to be, instead of, or we could just, because we usually do a sub 1 r to the n minus 1, don't we? But I can't do that here because this would be n minus 1. I can't do that. I have to say n minus 101. Because I'm not starting with a sub 1 really. This, you know what I'm saying? This is the real a sub 1.
Yeah.
So I have to do n minus 101. Because if I plug in 101, I get 101 minus 101, which is 0, right? So negative 1/2 to the 0 is 0, and then my first term is this.
Yeah.
Okay, sorry about that. Took me a minute to. But I wouldn't even go this far. You know what I'm saying? I would just say that the first term I'm throwing in the trash is negative 1 over 2 to the 101, right?
Mhm.
And so then that's what I put on top. But they have a positive number, so they're just doing the absolute value of it. But that's the one.
Okay. Thank you.
Yeah, I don't like how everybody felt on that last one. Yeah. Well, yeah, this part's really nice. This part's really nice. But then this one, you just have to get the maximum of this one. And that's not and the maximum here occurs at point, right? So what is 5 divided by 6? Diamond approximate. So the max is even, let's do this. Let's clear this, and we'll say, I want this, control copy, enter. So, I don't want it at 5, 6. I want it at, what was it? Point, 176326. 176326. That's pretty good for my memory there. And it's even bigger, Yeah. But yeah, tomorrow's just going to be very easy, much easier, or Tuesdays, much easier than that. Okay, so don't panic about this part. All right. Anybody else still there besides you, Tegan?
Just me.
Just you.